Potential energy is going to be equal to KQ over R, right? Negative. And does that infinity thing, right? So that's potential energy as you go for two charged particles. Okay? The voltage caused by a single charge. Sorry, let's do electric field first. The electric field caused by a single charge is equal to KQ over D squared, right? Or R squared, because we're using R. Okay? That's everything you need but the second charge you're putting in there, which is what an electric field is by definition, right? So that's my electric field for a single charge. Therefore, my voltage caused by a single charge would be equal to KQ over R with a minus sign in front. Single. So those are the formulas that we end up with. Okay. We also, by the way, said the integral of the electric field. Whoa, what the heck is that little thing I did there? It's not good. The integral of the electric field with respect to R is equal to voltage. And therefore, it's going to be negative because of the same game we're playing here. Fair enough?
In this chapter, are we going to be doing any actual calculus or sort of calculus?
No, we're setting up the field. Okay. Well, let me back up. Yes, you are. I'm going to make you do it. I'm going to give you some electric fields, hopefully today, as a function, and then ask you to integrate it to find the voltage. And I'll give you some voltages and ask you to take the derivative to get your electric field. Does that make sense? So there will be some, but they'll be fairly straightforward. Next chapter is where we're going to do, okay, because notice it's single. Charge arrays are seldom singletons, right? They're big piles of charges. So it's the big pile of charges, we're going to have to come up with something new for that. And that's what's coming next chapter. That is not the subject of this chapter. Okay? Fair enough? Make sense?
Yeah.
Okay, with that in mind, let's proceed forward. You guys said you're good through 11.5 because we did the electroscope together.
Yeah.
So we should be good through 11.5. So the 11.6 is the first one where we're going to have some trouble.
Yep.
What's the first one on that worksheet that you guys are struggling with? Okay, so there's a couple ways you can approach this. Traditionally, the first thing you have to find out is that force, regardless whichever way you approach it. The exception of that one you were trying to whatever, which is a little strange, but let's not do that. So I have parallel electric field strengths. I've got 100 with 1,000. So I know the electric field is equal to force per unit charge. So electric field times charge would be equal to my force. Agreed?
Oh, that's an F.
That's an F, yes. I realized that was weird. I took my fraction bar and turned it out. So 1,030 times the charge of an electron, which is 1.6 times 10 to the negative 19th. Agreed? And I get that the force being applied would be 1.65 times 10 to the negative 16th newtons. Agreed? Wait, disagree with that. It's a negative because it's going to stop. It's a retarding force, right? The retarding force still works like a force. So how far will electron travel in the field before coming to rest? Okay, so a couple ways I can approach this. I can approach this. You guys were talking about energy. You guys were talking about doing kinematics, right? So I'm going to do energy first, and then I'll do kinematics. Ready? Energy, I would go E. I would go, whoa. Energy before equals energy after. So energy before equals energy after, I would get the kinetic energy at the beginning. I have work at the end, right? So kinetic energy, I'm going to go 1/2 mv squared is equal to force times distance. Agreed? So then 1/2, the mass of electron is 9.11 times 10 to the negative 31st times the velocity, which is, what's the velocity starting with?
4.86 times 10 to the 6th.
Times 10 to the 6th equals the force, which we just said was 1.65 times 10 to the negative 16th times the distance.
Sounds squared, right?
That should be squared, yes. And so I slapped that on my calculator. 0.5 times 9.11 exponent negative 31st times 4.86 exponent 6 up squared divided by 1.65 exponent negative 16, and I get a lovely 0.065 meters. Is that correct? Okay. So that would be the energy, cheap way to do it. That works fine. I could also, by the way, approach it the way the Strauss said, which is, I mean, I could integrate the electric field they gave us, VR, for voltage, find the voltage VQ as energy, and plug it into this equation as well. I wouldn't do that myself, but that's something you could do. So let's do it kinematically. Kinematically, how would I approach this? Natalie?
I found the accelerator.
So F equals ma. So the force we have is 1.65 times 10 to the negative 16th. It's equal to the mass, which is 9.11 times 10 to the negative 31st, times the acceleration, right? What's my acceleration? Something ridiculous.
I got negative 1.809 times 10
It's to the 14th. And the negative you're applying because you say it's going the opposite direction. That's not something that's part of the math. Okay, so now that I have the acceleration, what do?
I get the velocity.
V equals V naught plus AT. Final velocity is 0. Initial velocity was 4.86 times 10 to the 6th.
Yeah.
Plus the acceleration, which is negative 1.809 times 10 to the 14th times t, right? And so I can bring that across. What do you get for time?
See, my answer is wrong.
Uh-oh. We're going to keep going. So I move that over. 4.86 exponent 6 divided by 1.809 exponent 14. So my time is equal to 2.687 times 10 to the negative 8 seconds. Agreed?
Yeah.
All right. That's bad news. Let's see here. Don't check your acceleration. Is that right? Ooh. 1.65 divided by 9.11. No, that was good. All right. Yes?
Oh, yeah, you're good.
Okay, so now I'm going to go d equals 1/2 at squared plus v naught t. The distance is equal to 1/2 the acceleration, which is negative 1.809 times 10 to the 14th, times the time, which is 2.687 times 10 to the negative 8th, squared, plus the initial velocity, which is 4.86 times 10 to the 6th, times the time, 2.687 times 10 to the negative 8th. Let's see what I get. I get let's do this again. 4.86 exponent 6 times 2.687 exponent negative 8 divided by 2. Yep, I get the same answer. Make sure you get that minus. Make sense both ways, guys? Can you do both? Can you see it? Is this not as foreign and alien looking?
I was doing it the first way, but I messed
One
up on the
question about
first
energy.
part.
Did you use, on the other side, not the work side, did you just use kinetic energy?
No. I just used
That's all I
F
see is
equals
minus
ma.
equal to the negative.
F equals ma.
Yeah.
Wait, what are you talking about? Over here? Yeah, this is kinetic. 1/2 mv squared
And even,
equals work.
well, okay,
The kinetic energy I have has to be depleted as work, right? On the other side.
sounds good to me.
And then since I got force, I can solve for the distance. Got it yet?
I really did get that answer.
You really did get that answer.
I got 6.4. A while ago.
6.4 meters. Huh. So you're still not getting that answer. Well, this is 6 times negative 8, so it should give you times negative 2. So there's no way you can get up to 6.4. So something's wrong with your times 10 to.
The other side of the equation.
This is going to be negative 16 once you square it,
Yeah.
times a 14.
It does.
So that'd be negative 2 as well.
Oh, shoot. Ira, that's a 6.
Ah, there you go. And if you divide your answer by 100, you get 0.064, which is darn close to the right answer, and probably close enough we can worry about rounding later. Okay, so far so good? Let's do B. How much time will elapse? Well, I solved for the time, didn't I?
Yeah,
Done. I solved for the time.
Oh yeah.
See this
see,
problem.
I was gonna do that way after I couldn't do the quadratic. This stupid piece of crap.
I'm gonna say red quadratic and Rusty's head just snapped over here. It was very interesting.
So there's the time, right?
So I'm pretty
So I'm
sure
done with that?
And then I was literally setting it up like
And
that,
then
so
C,
it's
electric
fine.
field ends abruptly at 7.88 millimeters. So 7.88 millimeters. So that would be 0.00788, right? What fraction of the initial kinetic energy will the electron lose in traversing it?
Yeah, see. I was right.
Time to approach that, Colin.
pretty wrong with me. That may just be the red pen.
The red pen.
Energy before is energy after.
Well, yeah. Yeah. The truth of the matter is you would probably approach it from the point of view of what was my force? You guys remember what the force is?
Well, how do you get out of here?
1.648 times 10 to the negative 16, or somewhere around there.
Okay. Times the distance, which is 0.00788. That would be how much work is being done, right?
So you do kinetic energy minus work.
So I do kinetic energy minus work over kinetic energy.
Oh, yeah.
Fraction of kinetic energy would the electron lose during trans. Yeah, that's. No, it wouldn't be. It would lose this much, just the work divided by kinetic energy, right?
If I found kinetic energy at the end and
Right.
divided by the kinetic energy at the beginning.
That's not how much it loses. That's how much did it lose. What percent did it lose? So I'd have to take the amount I lost, which would be the work divided by the kinetic energy. So the question's phrased. It's just the way the question is phrased for things. Good?